With that, let me say that we are very happy to have Professor Vijayaraghavan come from TIFR, and he will be giving us 3 lectures here on quantum superconducting qubits.
Thank you. Good morning, everyone. It's a pleasure to be here, and it's always great to come back to Bangalore and the nice weather. Thanks to the organizers for inviting me. What I'm planning to do over the next 3 lectures is to give you really a flavor of this field which uses superconducting electrical circuits for quantum experiments. I'll be focusing on 2 aspects. One is, of course, the quantum computing part. But also I will try to give you an example of what kind of experiments are being done which are more sort of physics oriented, and why this platform actually allows you to do these experiments quite nicely. And those things will become clear as we go along these 3 lectures. In the first lecture today, it's sort of going to be a relatively fast overview of the entire architecture itself. What is the superconducting circuit? How do you actually make it? How do you measure it? What are the typical problems one faces? And that hopefully will sort of give you an overview of the different facets of the research that happens in the different areas. This is again a very vast field now, exponentially larger than the time when I started my PhD more than 20 years ago. And hopefully this will give you a quick overview. So apologies to the experts here, because this will be, the first one will not be a very detailed talk in terms of mathematical details and technical details, but it will sort of take you through the entire gamut of activities that one needs to do in order to do experiments in this field. And in the next 2 lectures, I will delve into more details about specific experiments, specific physics ideas, specific challenges for implementing, using these systems for making quantum computers. Okay, all right, so with that, let me get started. Feel free to raise your hands or ask questions during the talk. I will try to stop about 15 minutes or 10 minutes before the actual end time, and then we can have an extended session, but do ask questions as we go along the way. Okay, so before we delve into superconducting circuits itself, and there are other talks on quantum information, so the first few slides might be somewhat repetitive, but just to be complete, the basic idea in all of this is that we're trying to play around with a quantum 2-level system. And you can just write them like this. And a convenient way of visualizing them is on the block sphere, and I'm sure most of you are familiar with this. The parameterization allows you to represent a 2-level state on a sphere, unit sphere, which we call the block sphere. The poles of these spheres represent the eigenstates 0 and 1. And because these are quantum 2-level systems, you can create arbitrary superpositions of these, and that corresponds to different values of theta and phi. So for example, 0 can be like this, 1 can be like this, and an equal superposition state can be represented as a vector which is on the equator. And of course, as you see, there are infinite number of possibilities of creating these superpositions because these theta and phi are continuous variables here. And that's sort of one of the first features, that a quantum 2-level system can be prepared in these superposition states. And there are these infinitely many possibilities to prepare such states, right? But a common misconception, hopefully not amongst most of you here, is this is often interpreted incorrectly, that this means you can store infinite amount of information in this particular system, because it looks like I can assign so many different points on this vector and assign it to some quantity. But unfortunately, that doesn't work, because you have to look at what information you can recover from this. And as most of us know, that when you measure a superposition state and you ask this question, what state you are or what energy you have, you only get 2 answers. That is, the state 0 will give you answer 0, and the state 1 will give you answer 1. But it will be a random answer to make matters worse, if you're really thinking of this as an excellent memory. And the probabilities are related to the coefficients of the superposition, right? So it's important to know that there are infinite possibilities for encoding, but you can recover only really 1 bit of information. So if you now extend this idea, and I'm sure there are other lectures which will elaborate on this in much more detail, where you extend this idea to multiple qubits and you say that, look, if you have an n-bit classical register, you can only program it into one of the 2 to the n possible states that exist. But with n qubits, it's actually possible to create a superposition of all the 2 to the n possibilities at the same time. Again, it doesn't mean there's much more memory in principle for storage, but it allows you access to a vast, much more number of states than you could do, like enormously larger number of states you can do with a classical bit. And in principle, when you operate on this giant system, many states are getting manipulated at the same time. And that sort of very hand-wavingly tells you why a quantum algorithm could do many more fantastic things than what a classical computer could do, is that this ability to operate on a vast number of states, which we call as the Hilbert space, but with the caveat that measurement only provides n bit of information. So you have to exploit the fact that these are solutions to a wave functions, so you can have interference going on. So an algorithm needs to navigate through this space in such a way that at the end you get some meaningful result and not some random zeros and ones which have no meaning to the problem you're trying to solve. Okay, so this is what one needs to do. There are other experts who will probably talk about how does one even write this algorithm. It is not obvious at all. There's no simple formula which says here, do this, and you can convert a classical algorithm into a much superior quantum algorithm. And this is a very active research field, not my core area of expertise. So if you now try to summarize a very basic set of requirements, and I'm sure many of you have heard about the DiVincenzo criteria. This is a much smaller subset, just sort of giving you, okay, you need some 2-level system which you can manipulate and create arbitrary states. You also need to be able to measure the result of this system very precisely. This might seem like an obvious thing, but a good part of my research career went in solving this problem for superconducting qubits. Because these systems are so fragile, measurement is not so trivial. You can actually have lots of errors in the sense that a qubit is really in the 0 state, but your measurement indicates otherwise. Or you have created a 50-50 superposition, but your measurement distribution is giving you something else. So you have to do it very careful. And in the later lectures, I will spend some time on the measurement problem in superconducting qubits. And finally, most importantly, you have to be able to make at least some of these qubits interact with each other. And that's actually how you can create and access all of these different states. And you will see in a little bit what I mean by that. Okay. So what's really the problem? This looks fairly straightforward. The problem is that pretty much any qubit we know today is unstable. What does that mean? Is that let's say you prepare a single qubit in an excited state. Over some characteristic time scale, it wants to relax back to this ground state. Right? Now think of this as a memory in the classical sense. You took some notes in your computer in this lecture, you went back home, you plugged in, you opened your computer, and all the data is gone. Right? That's really what is happening. So it's a terrible memory. And the typical time scale for this is in the tens or hundreds of microseconds, maybe up to a millisecond to a second, depending on which platform you're using to build the qubit. That doesn't sound great. If you save this lecture, you would like to have it for ideally for your lifetime at least. Right? So this happens over some time scales. And there is also another problem, which is another kind of decoherence mechanism. But this relaxation process is typically related to some kind of dissipation in the system. It will become more explicit when I talk about superconducting circuits. But then there is also another kind of noise process that can affect your quantum bit, is this fact that when you create a superposition, of course, this superposition can also decay to the ground state through the relaxation process, but it can also undergo another kind of process. Its angle, which is very important to define what superposition is it, can get randomized. So you started by creating a vector which is pointing this way, but over some characteristic time scale, it could be pointing any other way. And this process is typically called dephasing. And this is again typically due to fluctuations in your energy levels itself. So we call them frequency fluctuations, because the frequency which is corresponding to the energy difference fluctuates slowly over time. And that basically means that you no longer know exactly what the Larmor frequency of this two-level qubit is. So over some characteristic time scale, you have no idea where this vector is pointing. And if you think about what is required in that simplistic picture of a quantum algorithm, you need to be able to manipulate these vectors very precisely according to the instructions you're giving. So in some sense, you know where they should be. And if random processes cause these things, then you have no longer any idea what the state is. So, yes.
I thought that the graphic way to describe this dephasing would be that you started with a pure state on the Bloch sphere, and you end up inside the Bloch sphere.
Yes. So there are various ways of talking about what happens in the ensemble picture. So for example, if I average all of these vectors, so what I'm plotting here, by the way, let me, I think thanks for that question, Yuval. I don't mean that this vector has now become a superposition of 10 different vectors pointing in different ways. What I mean is that over many iterations, sometimes it could end up here, sometimes it could end up here. And what Yuval is pointing out is that one way of representing that is that you could average all of those, which is typically how we represent in the density matrix formalism. And in the Bloch sphere picture, if you average a bunch of vectors pointing in random directions in all possible directions, it will be a dot in the middle of the Bloch sphere. The more random it gets, the closer to the center it will get. And that is one way of looking at these things. So I'm just giving a few different trajectories, for example. Yeah, so these frequency fluctuations give rise to these kind of processes. And looking at this, it looks like you have no hope, because how do you stop this? There's a lot of research going on to extend these times to as long as possible. But luckily, turns out there is a solution, which is called quantum error correction, where despite working with systems like this, you can preserve the quantum state perfectly. But what you have to do is you have to use many such physical systems, so many qubits, physical qubits, to represent an effective logical qubit. And I think next week there are lectures starting on quantum error correction, which will elaborate on these ideas. But this was sort of really the theoretical development which showed that such a thing is possible in quantum bits, is sort of what really gave hope that we may someday be able to build a practical quantum processor which is not going to be affected by these kind of processes. Okay.
I have a question.
Yeah.
That you show that atomic state. So when you put the system for a longer time, it may happen the electron will make a transition from 1 to 0.
Yes.
Because it is unstable at 1. So in that way, it will emit some energy. So that energy can be in form of photon. Yes. So that is at the atomic level. But in coming to this qubit thing, the energy released, I mean, the up can go to down. In what form of energy it can go?
Okay, thanks for the question. So right now, this atomic state logo is just really a cartoon representation that it could be an atomic state. I have not really talked about what exactly is the physical system. We will go on to that. Simple, quick answer is it's a photon in that, in the case of superconducting qubits as well, it's just a much lower frequency photon. So we will see that in just a little bit. So remember, I have not talked about a specific physical.
I have a question. Yeah. So how is in classical systems, I mean classical processors, memory is preserved? I mean quantum system, I understood that what is the problem. But
you're saying why is there no problem in
classical system?
So it depends on what the kind of two-level systems one is using. Typically in a classical system, you don't have excited states. So you have something like a double well potential with very high barrier. And then if you are in this state, it is 0. If you are in this state, it is 1. And these barrier heights are so large, or equivalently, the noise which may cause this system to switch over is so small relative to the height that essentially it has an infinite lifetime. But by the way, this is not always true. There are some systems which require some kind of a refresh mechanism, which continuously sort of pushes the system back to its default state. So there are attempts in quantum computing also to come up with analogs of these systems which are highly stable, in general, you pay a price that if you make the system too stable, it's equally difficult to change it. And then there is a problem because you want to do gates, which is basically the changing of these systems. And that's sort of a price you pay. Maybe to summarize, quantum systems behave quantum mechanically if you sort of isolate them perfectly. But if you isolate them perfectly, you cannot do anything to them as well. So a lot of the game is to find the right compromise, that when we are able to isolate them sufficiently that it's stable for long periods of time, but at the same time, it doesn't become technologically difficult or even, in some cases, some physical limitations of how you can change the states. So for example, topological quantum computers are supposed to, the mechanism for changing them from one state to another is very different from how we do it for other kinds of systems. And the general idea is that you don't use excited states. Here, both of these are sort of ground states of the system. So then they are stable. That really depends on the particular physical system. T5 and T1 need not be related at all. They could be completely different. Usually we measure in an experiment a combination of these, and you will see that towards the end of the lecture. But it really depends on the particular physical system which determines the noise processes which control these two. Okay, yes?
So if you just prepare an X eigenstate, if we just prepare an X eigenstate and that starts precessing, that will not call dephasing, right? So what you are calling dephasing is uncontrolled time evolution. Is that
Right.
correct?
Okay. Yes. So Larmor precision, again, it sort of boils down to how I'm drawing the block sphere. Typically, I assume that I'm in the frame which is rotating at the Larmor frequency. That's why these vectors are stationary. You can equivalently say that I'm in the lab frame and then this vector is now rotating exactly at the Larmor frequency. And that's the problem there, that if now that Larmor frequency fluctuates in time randomly, I no longer know where it is. It's like a clock is moving, but it's moving at random speed. So I cannot predict where it's going to end up. So in this picture, when you're in the rotating frame at the Larmor frequency, what will happen is you'll have slow drifts of where this is pointing. So that is not dephasing. Yeah. Okay, so as I said, quantum error correction is sort of a very key milestone, and it's still not really achieved. There have been several proof of principle demonstrations, including some very recent ones which look very promising. But in terms of really being able to preserve a state unconditionally for an arbitrarily long amount of time is still not done. And it's a major goal across all platforms. And I firmly believe that till we solve this particular problem, we're not going to really make practically useful quantum computers. Because what this essentially means is that any useful calculation you can do has to be much shorter, has to execute for a period which is much shorter than these time scales. Otherwise, you can't really trust the results you're getting from the system. Okay. All right. Now, keeping these things in mind, if you now think about what a quantum computer really is, again, in the simplistic picture, it looks very, very straightforward. It's a network of physical qubits. Here, each circle is representing some physical qubit. I could put it in a linear array like that. I could put it in a square lattice like this. And that's really what it is. And you might have seen some pictures of quantum processors, and many of them do look like these, but not always in this simple way. If I talk about the requirements I mentioned earlier, you need the ability to do local qubit operations, which means that I should be able to address each of these qubits and change its state. So these are the single qubit operations. But you also need these multi-qubit operations, sometimes also referred to as entangling operations, and that's a critical requirement. And here, how the qubits are laid out plays a role. So these red connections are sort of giving you a rough idea that those are probably the qubits which are interacting with each other. So there's always nearest neighbor. In a linear chain, each qubit is interacting with two nearest neighbors if it's in the middle. And in a lattice like this, it is interacting with four nearest neighbors. And maybe only you can do those operations with respect to those pairs of qubits. So nearest neighbor turns out is sufficient. So there are theoretical proofs which says that any generic quantum algorithm or a unitary operation can be broken up in such a way that with only nearest neighbor interactions, you can actually execute it. But extended connectivity is actually useful, practically useful. What do I mean by that is that in this square lattice, if I wanted to do some kind of an entangling operation between this qubit here and this qubit here, the only way to do it in this architecture is that I have to go through many different intermediate qubits. And that means that in order to do an operation which would have been one step, I have to do many, many steps. And in today's world where error correction is still not there, it means you pay a price. There is a chance that the error of an entangling operation between two nearest neighbors is much lower than something if you're trying to do the gates across the thing. So having extended connectivity is useful. And I will talk about this later, maybe towards the third lecture of how one could do that. So here is an example of one of IBM's qubit designs. This one is IBM Washington. And it again tells you how the qubits are laid out. So this is a particular choice they have made. So you see that it's actually looks like a linear array, which is just winding with a few cross connections in between. Okay. And seems like a very strange choice when you look at it, but they did it for a very specific reason. It's a compromise. It turns out that in the architecture they are using, if you make the qubits interact, too many qubits interact with each other, it introduces other kinds of errors. Whereas having them not so heavily connected gives you this problem, which I mentioned that, if I want to make this qubit interact with this one, you're going to have way too many steps. So what they found was a compromise, which gave them overall a best result. And that's the reason they have chosen. So there are choices like these which are being made in how to lay out these qubits so that you get the best bang for your buck with today's problems. These are not fundamental issues. And once we solve some of these issues, we'll have many, many more possible architectures. This, for example, was very different than Google's processor on which the quantum advantage experiments were done. Very different layout. And again, for different reason. Okay. So then finally, you need the ability to do local measurements, which means that again, in this network of qubits, I should be able to address each qubit individually and determine the state of that qubit. And the challenges are the same. You have finite quantum coherence and scaling to a large number of qubits. This sometimes is not emphasized enough. A quantum computer will become useful only when there are sufficiently large number of qubits. We talked about this very large Hilbert space, this exponentially growing Hilbert space, that 2 to the n becomes large only when n is large. But that n can be very modest for a quantum computer. You must have heard these numbers that for n equal to 300, 2 to the 300 is roughly the number of atoms in the visible universe, right? So you don't need enormously large number of qubits to become very powerful. Again, a reference point, the Google's experiments, which used approximately 53 qubits, this 50 qubit number is approximately sort of a breaking point where you can just about manage to fit the requirements on the most powerful supercomputer, classical supercomputer you have. And this is the problem, right? If I have a 5 qubit quantum computer, your laptop is a much superior and an infinitely cheaper quantum computer than what you are actually going to use. Because you will be able to solve the equations of quantum mechanics exactly with no error on your laptop, whereas that multi-million-dollar 5 qubit quantum computer will make lots of mistakes. Okay, it's fun to play with, it's fun to build them. They are not really useful today as a replacement for something you can use. So only when 2 to the n becomes large enough that a quantum computer will become really powerful for using them for applications. If you're doing physics, you're trying to understand some quantum mechanical processes, smaller processes are also useful. Okay, so this. That's a good question. I thought before you finished your question, I thought you were going to say, why are they spending millions of dollars building them? You have to start building 5 before you build 500. So I think a couple of years ago, so when IBM first launched their 5 qubit quantum computer on the cloud, right? I mean, I was also surprised, like, what is this? Is it a joke? why would anyone want to use this? You can use your laptop. But I think it played a very important role. It caught the fancy of the entire world, students, the common man, that quantum computers are real. And you can, for free, play with them. Even though you're sitting in your laptop, you don't really know what is at the back end. So I think it did a big PR exercise, and I think that helped. There is also this belief, and though I think it's now dying down, that maybe if you let hundreds and thousands of people play around with a 5-qubit or a 20-qubit quantum computer, which still has errors, maybe you will discover something, and that could be useful. And this is essentially the promise of what called the NISQ architecture. But from some recent reports, and also from what I have seen, it's sort of dying down, even though a very recent IBM result again sort of emphasized that there is probably hope for the NISQ architecture. So just to maybe elaborate, this is the state where we are not doing error corrections. Your systems are prone to errors, right? And the question was, with a sufficiently large number of qubits, maybe, because remember, there are not that many quantum algorithms. There are a handful of them, and most of them cannot be implemented very effectively with the current error rates to give you any meaningful results. So there was this hope that if you sort of democratize this in some sense, give access, maybe lots of clever people will record. I think it has not panned out in the sense of finding an application. Again, let me emphasize very clearly, I'm not saying they're not useful in general for education, for research, but is it at a state where some company or a government is just, look, I've been using this old technology, I have a better solution, I'm going to replace it, and I'm going to spend the necessary money to do that. That has not happened. And there is, I think, sort of diminishing hope that NISQ architectures will be able to do that, unless there is a breakthrough in some coherence time and maybe you just reach the limits. There are some possibilities in these quantum chemistry kind of applications where, with these error mitigation techniques, where essentially you sort of understand the errors in your system, and from that you can undo the effects and make some predictions, but it's still not there. Others are buying them for the sake of PR exercises. There are handshakes between governments, and you say, hey, I have a quantum computer next to my lab. So, there are various reasons for doing this. But, at the level of 5 qubits, I think it's just a toy. But at the level of 20, 100, it becomes a very interesting, unique physical platform, which doesn't exist in a different form, right? One can say that, okay, maybe I can build a classical simulator of 100 qubits, including the fact that there are errors, but it's not so easy. So if that becomes a platform for doing interesting physics, exploring how decoherence works, then it's very useful. But is it going to, break RSA code? No, right? That's not going to happen.
But there is another thing.
Yeah.
There are people now. Yeah, now there is another aspect, because now people are trying to develop hybrid algorithms. So this is just using classical supercomputers together with quantum computers.
That's
so right. Where they are essentially optimizing using the quantum computing part, those parts which are hard, NP hard, okay, or those parts where you can speed up efficiently because you have a quantum Fourier transform, or you have some sort of algorithm of this kind, and then all the rest is done classical.
Yes.
So there is some hope that in that way you can solve much more important problems. So there are other kind of people are thinking other.
That's right. I mean, I sort of include this even though I didn't specifically mention, and I would imagine that any realistic heavy duty calculation is going to involve a combination of conventional classical calculations and a quantum version. But to the best of my knowledge, till today, again, in terms of showing a clear advantage over conventional methods has not yet happened. And this is again limited by the kind of errors you have, but there is a very strong effort in combining high performance computing systems with what they call as quantum accelerators. So do a bit of the calculation on the quantum part, and hopefully the errors there are not going to kill your entire calculation. So there is probably more hope there in the near term of doing something useful. But again, this useful has to be characterized. It depends on who you're talking to, right? So as I said, if you're doing R&D, if you're doing proof of principle, you're looking at how these complex quantum systems behave, they're very useful. Are they going to be economically useful so that somebody says, I'm going to now move to the solution? We have not reached there, but maybe with this hybrid approach, it could be one of the near-term successes. That's definitely possible.
Just saying,
yeah.
Justify his question.
Yes, yes, yeah, that's why. Yeah, see, I mean, I'll just say one more thing because we already had an extended discussion. I mean, it's a very interesting phase, right? I mean, even when it started, it's basically like a company is saying, you're the customer. And they're saying that, look, I have something which is not perfect, but maybe you and I can work together. You give me some money, but I'll give you a discount, but let's work together to see if this becomes useful. I mean, have we seen any other model there? But it's fantastic that if that can happen. And a lot of this is, because of the promise of what is eventually possible, and people want to get there first. And that there's an advantage there. Okay, all right. So let's move on with this.
What is this present state? Assuming you do single qubit operations, and there is a error rate. What is the largest system size you have right now, so that it doesn't exceed 50% error rate? Let's say, after which it's anyway useless. So what will be the typical system size?
I mean, the error rates are, it's not easy to characterize error rates in such a simple. Single qubit errors don't get worse as you make larger and larger number of qubits.
No,
but
if
typically not.
N operations,
yes,
then the cumulated thing will of course at some point hit 50%. So what I'm asking is, what's the typical dimension at which useless?
So this number is often what is referred to as circuit depth. And that again varies a little bit depending on the exact interqubit connectivity and the kind of algorithms you are executing. So
like the kind of thing which you showed just on slide.
Yeah.
What would be
I don't have a number off the top of my head for this. I mean, this one is a 128 qubit circuit, but
useful part might be much smaller, right?
no, it's not about that the only some part is useful. It's really about, in your algorithm, how many of these qubits you are accessing, which qubits need to have entangling gates between them. And that's actually the limiting factor.
So how many can you use without reaching 60 cycles?
60 cycles? Okay,
60 cycles.
yeah,
Okay.
yeah. Okay, so let's move on to the hardware platforms. There are many ways of doing this, and I'm sure you're aware one can use trapped ions and use the electronic states, long-lived electronic states. You can confine an electron in a two-dimensional electron gas and use a magnetic field to create a Zeeman splitting and sort of create a two-level system like that. That's the quantum dot or semiconducting qubit approach. And then in a superconducting circuit, you actually build electronic circuits operating at extremely low temperatures, but the circuit topology gives rise to quantized energy levels. And in some sense, all of these are equivalent because they implement two-level states. There are different physical constraints, different challenges, different decoherence mechanisms. And this is only a few. There are many, many other possibilities, but these are probably the three most leading platforms, with sort of photons making a very strong comeback in the recent years. Okay, so what is this superconducting qubit? Okay, and here I've shown a picture of a pendulum, and that's because the classical description of this simplest superconducting qubit has the same equations of motion of a pendulum. It's an oscillator, but critically, it's a nonlinear oscillator. Again, most of the time in high school, we study the pendulum as a linear oscillator because we do this approximation of sine theta equal to theta for small angles. But if you don't do that, it's actually a nonlinear oscillator. And this is the circuit which is representing the superconducting qubit. What it is really is a simple inductor capacitor in parallel creating an LC oscillator. Again, a system which you all have encountered at some point of time. The symbol here, the cross, represents a superconducting device called the Josephson tunnel junction. There are two of them. I'll tell you why you need two of them in some cases. And this is actually how a device may look like. I want you to pay attention to the size scales here. And this is also the design of the most commonly used qubit, which is called the transmon qubit. So these are the qubits which are used in IBM's processors and Google's processors. They are not necessarily this shape. This is a device from our lab, for example. And in the middle, you see this little square here. There is a zoom picture of this. This is basically this circle with two crosses. And this region here, where the laser is pointing, if I now zoom in, it looks like this. What you're seeing is two films of aluminum, which is the superconducting material here at sufficiently low temperatures. And there's a little overlap region where these two overlap. And between them, there is a very thin layer of aluminum oxide. So it's a metal insulator metal tunnel junction. But at low temperatures, it's a superconductor insulator superconductor tunnel junction. That's what a Josephson junction is. And electrically, it behaves like an inductor or a nonlinear inductor, just in the same spirit as how a pendulum is nonlinear for large excitations, right? When theta is not small. Yeah.
The Josephson junction is always a point-like object, or it has some special coordinate?
Oh, so this here, this boundary here, roughly what I'm tracing, is typically for a transmon qubit about 300 nanometers by 300 nanometers. It's not point-like, definitely not point-like.
So you have both X and Y coordinates?
Mm-hmm. Yeah, it's typically like a square or a rectangular overlap area. You can have other shapes. Some people make circles these days as well. But essentially, it's an area. And in fact, the area is what controls the inductance value of this nonlinear inductor. So you need to decide on the parameters before you make the device. Yeah.
How does it compare with the coherence
of the?
I mean, if I square the coherence length.
So remember, this is not a micro bridge or a nano bridge kind of Josephson junction. It's a tunnel junction. So the tunneling barrier is very, very thin. So the coherence length is now much longer than the barrier. So this is, so in the limit you're talking about, when your coherence length is comparable, then you don't get the sinusoidal current phase relationship, but you will get something in between. I mean, it's still nonlinear, but not exactly sinusoidal. So here you are in the limit is that you assume the transmission is occurring through large number of weakly transmitting channels. That's the limit in which a Josephson tunnel junction works. That is the point contact version where you have only one transmitting channel. That doesn't happen in this particular case. Yeah.
Now, what sense is the Josephson junction inductor? So when I think of inductor, I have some lumped circuit element kind of picture where I have the energy dependence going as I squared and coupling as L, or the current response and voltage response. So in what sense is the Josephson current has some I squared kind of thing?
That's right. So the current and voltage across this device have a relationship which looks like an inductor, but it's not linear. So for example, in an inductor, the energy is proportional to only the square of the current, right? Or the square of the flux. For this thing, there will be higher order terms as well. So I will be going through that part in the next lecture when I go into detail into the circuits. So I will answer that at that point in time. But yes, it's purely based on how the current and voltage across this device are related to each other. So here so that's the inductor part, and the capacitance is just from these two metal, these square metal thin films which are close to each other, and that forms the capacitor. So it's not really like a parallel plate capacitor, it's more like a planar capacitor, but you can just imagine electric fields between these two pads, and that gives you the capacitance. So you control that size to give you the correct resonant frequency you're interested in. So as I said, pay attention to the size. This device is nearly like millimeter size scale. You can see it with your naked eye. Yet, compare that to, say, an atom in an ion trap or an effective electron in a quantum dot, This is why often these things are also called macroscopic, quantum circuits. These are very big in size, involving, lots and lots of electrons and atoms, but yet under the right conditions, it can show you a quantized degree of freedom, which you can use and use as a qubit and manipulate as a qubit.
I have a question.
Yes.
I have a question.
Yes.
For the nonlinear inductance, do we see any such diode effect?
Diode effect, not in the regime we typically work in. The way you have to think about this nonlinearity is that in the sense of the pendulum. So what happens when you make a pendulum oscillate with larger amplitude, right? It still executes periodic motion, but now the time period is no longer independent of the amplitude, right? When you do this calculation with sine theta equal to theta, you get an expression for a time period which has no dependence on amplitude. But when you include that, you will see that as you increase the amplitude, the restoring force is actually becoming smaller because it's going as sine theta and not as theta. So the restoring force is less, so it takes longer to execute the oscillation. So the time period goes up or the frequency goes down. So in the same sense, in the regime we are working in, you are experiencing a frequency shift.
And I have another question.
Yeah.
That when we encounter Josephson junction, we have this entry bound states and all, right? So in this case, how the entry bound states will be modified?
No, so this is a tunnel junction just like any. So the Andrew bond states don't particularly play much of a role in this description. This you can solve by the overlap of wave function. In fact, there is a intuitive calculation in Feynman's lecture, I think volume 3, where they tell you how this sign thing comes about. But Brian Josephson, who won the Nobel Prize for this discovery, wrote down the current, what we call as the current phase relationship of this kind of a superconducting tunnel junction. And from there, you can, with a few manipulations, which I'll show you in the next lecture, you can get the expression for the inductance and how it's nonlinear.
What is the smallest out of all these different technologies, the smallest sizes that you can?
You mean in superconducting or all of them?
No, just the transmon itself. So what is the smallest transmon you can build that is still functioning?
So
with a non-material.
Okay, so I guess maybe my comment about the size, it's not required that I have to make it big. I'm just pointing out a side fact that it's big, yet it can be quantum. Now, strangely enough, when superconducting qubits were first being made, they were being made much, much smaller than this, and in fact, it was emphasized as a feature, very compact. It turns out that designing such compact circuits has a drawback in terms of microwave frequency losses. And this has got to do with how electric fields are distributed between these metallic plates, where are the loss mechanisms. So the modern day qubits, so by the way, this particular size is very big because this is typically used for something called the 3D architecture, where you work with big size systems where your microwave cavities are also big and they're actually machined out of metal, as opposed to everything being integrated circuit. So a typical qubit, which is say used in an IBM or a Google processor, is about maybe 4 or 5 times smaller in size, just because of the way the capacitor is designed. The parameter is the same. So what I may mean that the L and the C you need is the same. The Josephson junction size is not going to be very different because there is there's a trade-off. See, the tunnel resistance is what determines the inductance, and that depends on the area of overlap and the thickness of the tunneling barrier. One is linearly proportional to the area, the other is exponentially proportional to the distance. So there's a sweet spot where most people work, which means that once that is fixed, the area of the junction is more or less fixed because the inductance and the frequencies are fixed, because that's a good range of frequencies when it works. So the only scope you have, but remember that size can be maybe less than a micron, the Josephson junction. Then the capacitors can be made more compact, but today they are deliberately made bigger because of these loss problems. And I think I will probably touch upon these loss mechanisms in the third lecture, so it will become a little bit more clear on why we don't want to make them smaller. So there is currently no effort really to make it compact, because we are not trying to miniaturize these things to get them to work. That's not the immediate goal. We would like to get them to work in whatever size they can. And then one can think about making them more and more compact. So this was sort of a surprise discovery about 10 years ago, that people made these big circuits accidentally, and then they realized that they work much better. And then that led to the understanding of why it is better, and it led to optimization of the overall sizes. But there is no, you can make them smaller if you want. At some point, even the Josephson junctions can be made smaller if you use different superconductors, but then there are practical difficulties of electron beam lithography. Even at this 300 nanometer scale, it doesn't give you a perfect area. You might target an area of 1, but you will get plus minus 5% variation from device to device. So you don't want to make it much smaller anyway with the current technology.
So,
eventually, if you want to make it
Yeah.
these are practical questions that you need to
Yeah.
how far you can go.
But I don't see why the fault tolerance will be connected directly with the size. As of now, exactly. You will need more qubits, but there are ways of doing that. So at least to the best of my knowledge, we are not trying to find a way to make them smaller. There have been some papers of making more compact capacitors, but they're all, right now much, much lossier than what we can make with this technique. Large number of qubits necessarily, I don't think it means that it has to be smaller. The simple answer is that it turns out that the Josephson tunnel element, the oxide, aluminum oxide is the most stable. People have tried other things. It just doesn't work as well as aluminum oxide. It is, but it's sort of in the right spot for the kind of parameters you need for superconducting qubits.
So
Okay.
I have one question.
Okay, I think I'm going to not go through this lecture at all. All right. Yeah.
How is this anharmonicity tuned to give it a two-level structure?
That's the next slide. So let me go there then. Okay, so what is the qubit actually? It's really this oscillator where we use oscillations with different energy as the different states of the qubit, right? So the state 0 is the oscillator with 0 quanta. That means it's in its quantum ground state. And state 1 is the oscillator with 1 quanta. That is the minimum energy we can excite it to, with the caveat that there is this 0-point fluctuations always in the system, just like any quantum system would have. So that's it. So, if you want a classical picture, this oscillator at rest is 0 state, and the oscillator oscillating with some very tiny energy is the 1 state, but more precisely, it's this. Okay. So here is the energy level structure of such a device. What you're seeing here is a cosinusoidal potential. So remember that a linear harmonic oscillator would have a parabolic potential, but because it's nonlinear and the form of the nonlinearity is, remember, is the same as a pendulum. Restoring force is proportional to sine, so the potential is proportional to cosine. So that's what this is, the cosine potential, and these are the quantized energy levels. And when you ask this question about what the nonlinearity does, is just like in a classical pendulum, the frequency of oscillation goes down as you increase the amplitude of oscillation. The frequency separation between these levels goes down as you go higher and higher in this ladder. So that makes these levels unequally spaced. And that is the reason why we can use it as a two-level system, because the typical way of playing with these systems is to shine light at the resonant frequency between these two levels. And now the other levels are off resonant, okay? And the unharmonicity is sort of given by the nonlinearity, the form of the nonlinearity, which is directly related to the sine function. So there is not too much you can do to tune the nonlinearity, except there's a scaling factor which comes from the capacitance. But if you have decided to make the qubits in a particular frequency range, you don't have too much room. And there is also another aspect which I will cover in more detail in the next lecture, that the sensitivity of this kind of a qubit to charge fluctuations in the substrate changes depending on what unharmonicity you choose. In fact, that was a big reason why this design was invented. And you can also see the typical parameters of the inductors and the capacitors, which are used for making such a device. And one needs to operate at very low temperatures such that thermal energy is much, much smaller than the typical energy between the ground and the excited state. For the typical parameters shown here, which is what one uses, this resonant frequency is in the microwave regime of around 5 gigahertz. If you convert that into a temperature unit, it's about 250 millikelvin, so h bar omega over k Boltzmann. And then you operate in a dilution refrigerator, which takes you down to about 10 millikelvin so that you satisfy this condition. Why do you need this condition? It's because you don't want random thermal noise to cause changes in your state. Remember, you want to precisely control what the state of the system is. So ideally, in this condition, if you leave the system alone, you expect the system to end up in the ground state. And that's the starting point of any quantum computing algorithm or any physics experiment. You need to know where you start. If you have high temperature, even something of the order of 100 or 200 millikelvin, you will get a thermal distribution of these levels according to Maxwell-Boltzmann distribution. And that's really a mixed state. You don't want that. Okay. There are ways, if you do end up having that, there are ways to work around it, but I will not go into that detail. Okay.
Vijay, how large is omega 0.1?
I'll come to that. It's about 300 megahertz. So here, you can do that calculation. So yeah, it's like 2.5 or microkelvin into 300. So something like 750 microkelvin.
I have a question.
Yeah. Sorry, let me just finish this.
I have
and
a
I'll take the
question.
question. I'll just finish this slide and
Okay.
I'll take the question. Okay. So as I said, we expect the system to be in the ground state, and I want to use this now to motivate why superconductors, right? Remember classical pendulum, you set it to oscillation. What happens after some point of time? It stops oscillating. Why? Because it dissipated its energy through whatever dissipation mechanism was there. The equivalent picture here is I put the system in the excited state. It will come back. That this is an electrical circuit, so it's some kind of resistance in the circuit. Remember, this circuit I've drawn, the way I have drawn it, there is no dissipation in it. These capacitors and inductors don't have any dissipation intrinsically in them the way I've drawn it. When I make them, of course, they are never going to behave like this. But that's the reason you use superconductors, because you can build these elements with the lowest possible dissipation you can get. Now, ideally, the superconducting metal itself, of course, should be dissipation free, but the dissipation comes from the substrate, from the oxide, which is growing on top of the aluminum, and various other factors. But this is sort of a way to motivate why superconductors are needed. Okay. All right, question here.
So if I remember correctly, for the LC circuit, there is a frequency 1 by square root of LC.
Yeah, that is 5 gigahertz.
Okay, so will it be comparable with that omega 01, omega 1?
Yes. To the lowest order, that's the simplest calculation you can do. But when you actually quantize, there's a small correction which comes from there. But that's why I gave these numbers. If you run the numbers, it will come out to be around 5 gigahertz. Okay. Sometimes I get asked, then why 5 gigahertz? You make it 50 gigahertz. You can operate at higher temperatures. There are various practical reasons for it. Microwave frequency instrumentation and control is infinitely harder if you go to 50 gigahertz as opposed to 5 gigahertz. It turns out this is a very, very convenient spot. This is called the C band in microwaves, 4 to 8 gigahertz. And I'm not joking here, but I think the choice of this frequency may have had a big impact on why this field developed rapidly. There were lots of off-the-shelf commercial electronics because of the telecom industry available, which were actually infinitely more superior in quality and stability than what was needed at that time and even now. And that led to a rapid progress in controlling these systems very, very precisely. To contrast this to systems which require lasers, it's much, much harder. You can today buy a microwave source, which is good enough to control a superconducting qubit, which just runs off USB power for like $1,000. It's extremely low cost, and lots of new technologies are coming in as well, as I will hopefully indicate soon. Okay. All right. So now coming to how does one actually control this state? As I said, typically you send in microwave frequency radiation resonant with this omega 01 transition. So this is sort of a cartoon representing a pulse like that. Again, you assume that you're starting with the ground state. And then we typically do an experiment where we send this pulse with varying length of time and then make a measurement. Okay, I have not told you how measurement is done. That's coming in the next slide, so just bear with me. And then you typically get a plot like this. What is plotted on the y-axis is the probability of finding the system in the excited state. So remember, these are again ensemble measurements. Each of these experiments is repeated thousands of times for a particular time length here. And then you plot the probability here and you get this oscillation. So what is this? This is the basic, very simple driven two-level system physics, which is often introduced as the first example of time-dependent perturbation theory. Right? That's what's going on here. You drive the system on resonance and the qubit evolves continuously from its ground state to its excited state and then back to the ground state and back to the excited state. Now, in an ideal case, this would have been perfect sinusoidal oscillations between 0 and 1 going on forever, right? The reason this doesn't happen is that in between, there are these random decoherence processes which are happening, which are resetting the phase of these oscillations. And that's why these exponentially, they decay. Right? So here's a first example of what decoherence does. And this phenomena is called Rabi oscillations. The amplitude of your pulse controls the frequency of this oscillation, so how fast it will rotate. So if you now go in the Bloch sphere, the phase of this microwave pulse. So what I mean by phase is that with respect to some chosen arbitrary time axis, whether it looks like a sine omega t or looks like a cosine omega t, that sort of determines on this Bloch sphere whether the rotation is going to happen along this axis or whether it's going to happen along that axis. Okay.
Question.
Yeah.
So you're measuring it even while you're driving it?
No, the measurement here is the readout pulse is after the measurement. There are experiments when one can do that. Maybe if I have time, I will talk about that in my last lecture.
So it's just free oscillation?
Yes, so the system is evolving freely, but I'm stopping the system at various time intervals and the measurement tells me what state I have ended up. Yes.
Sorry, can you say again, what is the source of the decay of this?
The source of the decay are these decoherence processes. So a very simple picture is that you're applying this drive, the system is evolving, but you had a decay event and that reset the system to the ground state. Now it will again start evolving from there, but now the phase of this new oscillation is no longer synchronized with the previous one. And since these are done in an ensemble fashion, each time you do, you will get some random evolution. But of course, one cannot observe that evolution individually. Those are called quantum trajectories, but you can't observe them directly here. But when you average them, you're essentially averaging sinusoidal functions, which are all in sync at the beginning, but slowly in time, they're off sync. Okay. So their phases are all messed up, so they average out. So if you continue this longer, you'll get a straight line, sort of horizontal line at 0.5.
Okay. No, but when you say in an ensemble fashion, do you measure a lot of qubits at once or measure one?
Same qubit over and over again, starting from the same initial condition. So all experiments, when I say ensemble in superconducting qubits, is always done on the same system. So it's an ensemble in time, but it's the same thing. You have to ensure that you're always starting in the same initial condition. Otherwise, this has no meaning.
Okay.
That we can ensure. So again, amplitude controls the frequency of oscillation. The phase controls the axis of rotation. So that gives you control over what kind of superposition you want to do. And the time of this pulse controls the amount of rotation, right? How much did you rotate? So with these things, you can now get a sense that I can now place this vector on the blocks wherever on the Bloch sphere I want. So I have sort of universal control on the single qubit state, subject to decoherence processes. So that's why you have to do them in a very short time as possible. Okay. So you can create any superposition state you want. Now, coming to the measurement part. In order to measure, we use this architecture called the circuit QED, which is sort of borrowed from the cavity QED, which is the physics of interaction of atom with light confined inside a cavity. In the case of atomic physics, it's typically a Fabry-Perot cavity and laser light. Here, it's a microwave oscillator. So here is your original qubit with Josephson junctions and capacitor, which is a nonlinear oscillator. And it is coupled to now a regular LC circuit, which is a linear oscillator. And this linear oscillator plays the role of a measurement cavity, right? And the two are coupled to each other with a capacitance, and that gives rise to an effective coupling strength G, which is sort of the rate at which they can exchange photons with each other. And the cavity itself is coupled to the outside environment with the rate kappa. This is the rate, this is sort of like the transparency of your Fabry-Perot mirror, right? How much light can leak out of the cavity. And that controls how fast you can manipulate the cavity and so on and so forth.
So
typically,
the pulse picture that you gave is only for single qubit gates, right? Can you do multi-qubits, like entangling qubits using pulses?
Yes, yes. Everything is, so, I mean, everything has to start and stop in time. So it's a pulse, right? If something is not a pulse, it has to be on for an infinite amount of time. So, but I see what there are protocols where you just turn on a drive and keep it on, which sort of stabilizes systems in various states. We are not talking about that right now. Okay. Now, one thing to keep in mind is that in this architecture, the frequency of resonance of this nonlinear oscillator and that of the linear oscillator are kept separate. So omega R is the cavity for the readout, omega Q is the frequency of the qubit, and they have to be detuned and much larger than the coupling strength between these two cavities. And when you do that, you get something called the dispersive shift. This is described by the Jaynes-Cumming Hamiltonian. In the next lecture, I will go through those details. And you get the fact that the frequency of this cavity now depends on the state of the qubit. So here is sort of shown a response function of this cavity. So this is a plotted reflected phase, which means I send in a microwave and the microwave scatters back with a phase shift, right? A typical question which often comes here is that why not look at absorption? In the ideal world, there is nothing to absorb power here. Note there are no resistors. It's a purely inductive or capacitive circuit. It cannot absorb microwave. And that's important. Yes?
Two questions. First of all, G has dimensions of omega. So
yes.
Is it some RC time? In which case you need to do some resistance?
No, this is not an RC time. So it's basically the G is defined in the way that if these two oscillators were on resonance, then they would exchange energy back and forth at this rate. That's what the definition of G. So the G comes from the Hamiltonian picture. In this picture, the G will be proportional to the capacitance, but also have factors which depend on the frequencies of these two things. The way you control is with this capacitor here. That tells you, so remember, if the capacitor was 0, then these two electrical oscillators are not interacting at all.
If G, just to make it dimensionally correct, G is a function of the capacitance.
Not only the capacitance. No. Well, you can also have inductance, right? To turn it into a frequency. Yeah. So I have not written the formula for what G is here. I will do that in the next lecture. But there is no resistance, no. Okay. Yeah.
The other one, you said that geometrically, the Josephson junction is not a point like it's an area.
Yes.
So actually, there are many bridges, many Josephson bridges.
Yes.
So the fact that you draw here two Josephsons is schematic. Actually, you mean
okay. So no, sorry. So the multiple weak transmitting barriers I'm talking about refers to only one junction. These two junctions, I now realize that I completely forgot to explain why there are two junctions. So these are two separate junctions. Just if I quickly go back to this picture, here you see there are, there is one junction here and another junction here, and there is a superconducting loop here. And what this allows you is that I can now apply a magnetic flux through this loop, and that allows me to tune the value of the inductance. Remember earlier I told you that the value of the inductance is set by the area, and you cannot change it once the device is made. This way, if you put two of them, this makes what is called a SQUID, or a superconducting quantum interference device. And that allows you to tune the resonant frequency. So now by applying a magnetic field, I can actually control omega 01 as well. So depending on the particular experiment, you either have two junctions or only have one junction if you don't want to tune it. So that's the reason. So this is not representing the multiple channels in the system. Okay, so, so when you scatter these microwaves, you get a phase shift as you go through resonance. And that's sort of the middle point here. And now you have two different resonance frequencies depending on whether this quantum system here is in the ground state or the excited state. And that now gives you a mechanism to measure the state of the qubit. Yeah.
You mentioned that there cannot be any absorption in this system. Therefore, you cannot measure absorption spectra. But I mean, an LC oscillator can absorb the energy, right? If you
LC oscillators can absorb the energy. I am talking about what I have drawn on the circuit here. Yeah. In steady state, okay, if you want to really get into the details, there will be some absorption of energy in the beginning when you are building up the energy in the system, but in the steady state, there is no dissipative element here. So whatever goes in comes out.
Yeah, but like, for example, if I have a cavity and I add 2 microwaves.
If you do the experiment, it will absorb. I'm specifically talking about, I'm now being a theorist. I'm saying, look, this is what I have drawn. There is no resistor here. Okay. This is actually, there is an important detail here, which is related to how good your measurement can be. You actually don't want that microwave to be absorbed by any component here because it actually kills your signal. Okay. So we make sure, and that the way we do that is by ensuring that the coupling to the environment. So there is dissipation, but it's to the environment, not to some uncontrolled degrees of freedom. And the environment is where you're collecting the photons. Okay. So I will go through some of these details in the later lecture, so it will become clear here. Okay. Maybe I should have not made that comment at this stage. So you have.
Current which flows there is a displacement. That's it. That's all that goes on.
Yeah, basically in inductors and capacitors, the current and the voltages are always 90 degrees with respect to each other, so they don't dissipate any energy. So the cavity frequency depends on the qubit state, and the qubit state measurements are implemented by a microwave pulse and measuring its phase shift. So what we do actually in reality is we send a microwave pulse at this frequency shown by this dashed line, and then depending on whether the qubit is in the ground state or the excited state, we get 2 different phase shifts. So scattering of the microwaves happens at 2 different phase shifts, and that is what you detect. So the phase tells you whether the qubit is in the ground state or the excited state. How does it look like in practice? This is what it looks like in practice. Okay. Just pay attention to one of the colors first. So the blue curve here is showing you a histogram of phase measurements. So the x-axis is, it says digitizer unit, but it's basically a proxy for the phase shift. So you can just think of this as a phase. It's giving you a distribution of phase values you have done for some hundreds and thousands of experiments. Okay, so it's a histogram. The y-axis is plotted in log scale. It's counts, but it's normalized, so it gives you probability. That's why instead of a Gaussian distribution you typically get for noisy processes, you're getting a parabola. In the log scale, it looks like a parabola. Right? So the first point to note here is that the distribution of all the phase values when the qubit is in the ground state is centered around this value here. Whereas for when the qubit is in the excited state, sorry, it's the other way around here, it's centered around here. And these 2 distributions are well separated from each other. Again, note that this is a log scale. So between this point and this point, there's like 2 orders of magnitude difference in the values. So if I had drawn them as Gaussians, they would be highly separated Gaussians. Why is this important? Because this means that my signal is not giving me any ambiguity in knowing whether the phase shift corresponds to the ground state or the phase shift corresponds to the excited state. These measurements require a specific kind of an amplifier made out of superconducting devices, which I worked a lot on during my PhD and postdoctoral days. And before this, before the invention of that thing, these width of these histograms would be several times the distance between these histograms. So you couldn't really know in a single measurement whether the qubit is in the ground state or the excited state. But you also see these other things. The blue histogram has a little smaller histogram on the excited state size and vice versa. These are false events. These are events where the qubit is undergoing a change of state during the measurement process. In fact, this is now an active area of research where people are trying to understand how to prevent these things from happening, because they also give rise to errors. But again, you have to note that this little bump here is 2 orders of magnitude lower than this one. So that's why this number 98.8% tells you how accurately you're able to distinguish 0 and 1 states. And 1 minus that is the error you're going to make in these systems. There are various, so the simplest mechanism is that the qubit in the excited state can just decay. If you have some thermal noise, the ground state can also get excited, and that gives you, but what happens is that in the presence of these microwave photons, there is some mixing of the qubit states which happen, which is actually caused by the microwave photons. So I will actually discuss this in some detail because this is an area I am working on actively right now in the later lectures. The simple version of the Hamiltonian says that such processes should not happen. But that's because it's an approximate Hamiltonian. There are higher order terms which kick in when you drive the system hard, and that causes these problems.
Can I ask a silly question? So how is it you determine the 98.86% exactly? How is it you do that?
So we measure this distribution with 100,000, a million counts. And then we calculate, because we know that I have created the ground state. So I know that my distribution should look like this, but I have some counts on the other side. So so ultimately what you do is you draw a discriminator line and you say everything to the left, I'm going to call as ground, everything to the right, I'm going to call as excited state. And then you count all the wrong counts you got for both 0 and 1, you add them up, divide by 2, and that's how you get this number. Are you asking why 2 places of decimals?
No, well, not only that, but I mean, why you call this fidelity? I mean, I'm trying to understand. I mean, fidelity with respect to what you know is the 0 and 1.
Exactly. Yeah. Yeah. So 1 minus that, or 1.2%, is the probability of measuring the state incorrectly.
0 or 1.
Yes, that's right. 0 or 1. Exactly.
Not an arbitrary state.
No, but you see, in an arbitrary state, when I measure, I still only measure 0 or 1, right?
I understand.
That is what you're talking about, is the fidelity associated with the preparation.
Yeah.
So there you have to do process tomography and various other things to characterize. This is much before that, because if this is messed up, I can't do any of the rest of the stuff very accurate. Yeah. Yes. Okay. Yeah. That's just for distinguishing 0 and 1. Okay. So once you have such good ability to discriminate, you can now actually see these quantum states evolve in real time. But okay, not all kinds of evolution. What's being plotted here is 6 different experiments where the system was first prepared in the excited state, and then we just kept the microwave on. Okay, we looked at the phase shift, but now we broke it up into small time windows and looked at the phase as a function of time in small bins. The bins are big enough that within each bin, these histograms are nicely separated. So that basically tells you you have good signal to noise ratio, and then you do it for an extended time. What you are seeing here are events when that quantum state has decided to decay from the excited state. So in this case, so these are 2 different experiments. So the phase shift here is sort of -40 and -20. The dashed lines sort of give you the reference point for what the phase should be for state 1 and state 0. And every one of them starts in the 1 state because we prepared the 1 state. And they all decayed back to the ground state in a jump-like fashion at random time distributions, because this decay process is a random process. Usually this will be like a Poisson distribution. So this is what is called quantum jumps. And back in 2011, we observed this for the first time when I was a postdoc at UC Berkeley. This particular data is from my lab now. But this was sort of the beginning of the very high SNR measurement era of superconducting qubits, that you can actually see these events happening in real time. As you were asking before, if there was some thermal noise, you would actually see them jump back to the excited state as well. Yes.
But I understand these jumps would be instantaneous, right? But here in the figures, there seems like a finite time where there's a finite slope.
Yes. So 2 comments. Some very recent research suggests that they are not really instantaneous. They're like fast, very fast, but they're not instantaneous. I will not comment more on that. But 2 here, it's the detector bandwidth which tells you. So the qubit changes state, then my cavity has to respond to reflect the phase shift. So that takes time. And what time is that? That is set by the kappa. That's the oscillator's line width. That is the time scale over which it will respond. So that's what gives the finite width of these transitions here. And remember, no instantaneous event is ever measurable, right? Everything is going to be limited by your experimental apparatus. So Yuval, you had a question?
So I'm looking at this lower panel, and I don't understand it. I mean, there are different curves, but each curve separately goes from state 1 to state 0.
Yes.
But not a reverse.
Yes.
I don't see the reverse.
But why would ground state go back to excited state? In general, it should not.
Yeah.
Sorry, I guess if there was some thermal noise, and it also depends on the time scale. So the thermal processes might just be much slower. So if I taken this data for like 10 times longer, you might have seen an occasional event going back up. I have not shown that here. All right. So my hour 15 is over. I have 15 minutes. Maybe I'll go on for another 5 minutes and then we can have questions, and then I'll pick up from there on. So this is actually sort of a good place to stop. So we now seen that we have the ability to measure, we have the ability to manipulate the single qubit state. So typically in the quantum circuit language, there are these discrete gates one talks about. So a NOT gate is just something which takes 0 to 1 and 1 back to 0. So these are rotations on the Bloch sphere of 180 degrees, right? So you choose a right pulse to do that, and that's how you implement a NOT gate. You have also something called the Hadamard gate, which will take a 0 state and create an equal superposition state. And in general, it takes 0 to 0 plus 1 and 1 into 0 minus 1. So these can be interpreted as rotations about an axis, which is sort of x plus z over 2 in this Bloch sphere. So in this way, the picture, if you think about, all single qubit gates are nothing but rotations on the Bloch sphere. And these single qubit gates are implemented by microwave pulses of the right amplitude, the right time, the right phase. That allows you to do these gates. Okay. So the last thing I will touch upon before we pause here is that how to think about multi-qubit gates, right? So here I have 2 qubits and I've written them in some arbitrary superposition parameterized by this alpha 1, beta 1, and alpha 2 and beta 2. If I now write the joint state, which is often called the product state, the general 2-qubit state can be written like this, where you just multiply these coefficients. You now have 4 basis states for a 2-qubit system. But the question is, if I want to create a state like this, gamma 00 plus eta 11, if I try to look at this state and I try to look at this general state here, and I say, hey, what values of alpha 1, beta 1, alpha 2, beta 2 I need in order to get this state, you will see that it's not possible to do that, right? Let's just take one quick example. So this says that the coefficients of 1, 0 and 0, 1 should be 0. So if I set alpha 1 to 0, then that will make this also 0. If I set beta 2 to 0, it will set this also to 0, and so on and so forth. So what this tells you is that if you have 2 independent qubits whose states are defined by these, there is no way by adjusting the value of alpha 1, beta 1 that you can create a state like this, because this is an entangled state. What this means is that single qubit rotations cannot take you to an entangled state. You need the qubits to interact and do something else in order to be able to create a state like this. Okay, so here is a simple example, and in the later lectures, I will give you specific protocols which allow you to do that, where the 2 qubits are labeled as C and T, which they typically stand for control and target. And the white colored ones are the state before the gate is applied. And the red colored ones is the state of the individual qubits after the gate is applied. And this is sort of like a Boolean truth table. So if both are in 0, they remain unchanged. If the control is in 0, target is in 1, then also they remain unchanged. If now the control is in 1, it applies a NOT gate to the target and the control remains the same. So 0 becomes 1 here and control remains the same. And again, if the control is 1, but now the target is 1, 1 becomes 0. Okay. This is, I have not told you how this is done, but I'm saying that if there was an operation which would do this, you can create a state like this. How is that? You prepare the control state in this alpha 0 plus eta 1. Okay, that's a single qubit state. You make the control qubit and you prepare this superposition with these coefficients and you leave the target at 0 and you apply this rule. And the way this rule has to be now extended, because this looks like a classical truth table, right? So for the quantum version, all you have to do is for every superposition component, you do the corresponding operation and replace it. Okay, so the state before is just gamma 00 plus gamma 10. So that corresponds to this one. So it will now flip the target to 1 and you will retain, so the 00 part remains the same, but the eta 10 here gets converted to eta 11. These kind of operations require the qubits to interact with each other, and only then you can do this. Okay. So I'll finish with this last slide. What does this interaction mean, right? So this is an electrical system, and I had already shown an example of interaction in the measurement protocol, where the non-linear cavity was coupled to the linear measurement cavity. Here, you take two nonlinear cavities and you couple them with a capacitor, for example. So this now looks again like a coupled pendulum, for example. Right? And that's more or less what you need to do. But of course, there are then the right sequences of pulses you have to apply to do the right operation. This can be a simple capacitor, or it could be a microwave frequency resonator, which is this, shown here, which is often referred to as a bus cavity. So in this picture from an IBM paper from 2016, these are the qubits here. So here you see that the capacitor shape is somewhat smaller. And these squiggly lines on the extreme sides are the measurement cavities. These are the Fabry-Perot version on chip. So these are transmission lines which have transparent mirrors on either side, which gives rise to resonator. And then the coupling is also mediated through such a resonator. And the reason for using these structures is that now you can keep the systems far apart. Because remember, if it had to be a capacitor, it typically needs to be close to each other. Because at microwave frequencies, you cannot just run a wire. There's no concept of a single wire at microwave frequencies. It will behave like a transmission line. So that's how you do this. This is called a fixed coupling architecture, because once you design it, the coupling strength between these qubits is sort of fixed by the geometry and how much capacitance you have put between them. You can also have other kinds of circuits. So this is a paper from the UC Santa Barbara group from back in 2014, but this is similar to the technology which is used in Google's processors as well. So now these capacitors of your qubit are plus shaped, okay, and the Josephson junctions are somewhere around here. And similarly, there's a second qubit over here. And this circuit in the middle has some inductance. It also has some Josephson junctions, which you can barely see. And with this control line, you can actually apply a magnetic flux and tune the coupling between these two interactions. So this actually allows you to turn the coupling on and off or change the strength of the coupling by applying the right control pulse. Okay. Again, not going to the detail today on how exactly these things are done. I will give some examples in the later lectures. So here you can actually turn the coupling on and off, whereas here there's always some coupling which is going to remain. And there are some pros and cons of this. The con here is, of course, that you need an extra control line, but the pro is that you can really disconnect the qubits. Whereas here, the qubits always have some interaction even when they are not supposed to be interacting. And this is actually the reason why IBM chose that loosely connected architecture. This remnant coupling gives rise to something called coherent errors. And they had to compromise because they used the fixed coupling architecture And they had to compromise between the coherent errors and the overall connectivity of the processor. Okay, so the general idea, and this is the last thing I'll say, is that we have to make the state evolution of one of the qubits dependent on the quantum state of the other qubit. That's the interaction which will give rise to these conditional operations and give rise to entangled states. So I'll pause there and I'll take questions and we'll continue next time.
Yeah. So when you try to produce entangled states, like superposed entangled states, so I'm here. Sorry. Yeah. So do you again do a Rabi oscillation? Like you start from 0, 0, you go to 1, 1, and you kind of catch it midway. Do you do the same thing again?
Yes. So that is what you're referring to, is the calibration operation of how we actually figure out what the gate is. So typically you will turn on some interactions and that will give rise to some combined evolution. You will stop that process. You will then measure the states to figure out what has happened. And then you'll repeat it for different parameters, which typically means sweeping a time and sometimes the amplitude. And then from that data, you know which particular set of parameters is going to give you the operation, the entangling operation you're interested in. So yes, some equivalent, we can't call it Rabi oscillation because it's some joint evolution of two qubits.
Okay. And one more question. This might be a very theoretic question. So when you're doing this Rabi oscillation from 0 to 1, and like ideally, like when it's not decohering and all, so after every oscillation, since it's going around the block sphere, does it pick up this geometric phase, and can you see it in your experiments?
Not in the single qubit space. There is no additional geometric phase which is implemented. But the moment you go to, remember that these systems are actually multi-level systems. There is a second excited state over there. And people have actually used that to do a Rabi oscillation between 1 and 2 and come back. And that gives rise to a phase. I think the simple reason, maybe someone can correct me, is that in the 2-level subspace, there is no extra reference to account for that phase. Now, when you have 3 levels, then you can account for that. In fact, one of the entangling gates uses this accumulated phase to implement a 2-qubit gate.
So you can read that phase, like in
Yes,
your experiments, you can detect that phase being.
I mean, you don't read it in the sense that you do a measurement and it gives you that accumulated phase. You make that phase do something else, and then you can indirectly infer that this has happened. Thanks. Yeah.
In the 1980s, it was popular to build Josephson junction arrays.
Yes.
And to bias each junction at half-flux quantum or something like that. Is that a viable setup, or is that?
Are you asked, was this being done for doing qubits or something else?
It was usually done not for qubits.
Yeah, so there are other qubit designs. Yeah. So now depending on this.
And those have actually many,
in my next lecture, I'm going to walk you through a few different qubit designs. So some qubit designs require this operation exactly at half-flux quantum. Yeah. But they are not just simple arrays. So there is one qubit called the fluxonium qubit. It actually uses an array of Josephson junction, but the purpose of that array is to actually implement a very high linear inductor. That's the main purpose of that. But it is part of a superconducting loop with a small junction and an array of junctions, and that has to be biased at half-flux quantum to be in the most optimal space for doing qubit operations. So there are some designs which are like that. Traditionally, I mean, I would say maybe before 10 years and earlier, there was this general notion that a circuit with more Josephson junctions is probably not going to be very good. Because there was this notion that the Josephson junction oxide barrier is amorphous, there may be losses. But this has turned out to be incorrect. Till now, we have not found that in any qubit design, the coherence is limited because of the amorphous nature of the Josephson tunnel element itself. So now there are experiments which use arrays of Josephson junction up to 100 and several hundred, and they are one of the most coherent devices which have been measured so far. Yeah.
So to follow up on your question, Eduardo. I think that two things. First, I think it would be very useful, perhaps next time, to see a table which compares different designs like fluxonium versus transmon, the pluses and the minuses.
Yes.
And the other point is that back in the 1980s, there was an effort, at least by IBM, to build a Josephson computer. It was a classical computer.
That's an analog computer, yes.
But analog computer, and they put hundreds of millions of dollars of 1980s, not of today, in this project, and eventually they folded it because the accuracy was undermined by the exponential sensitivity of the tunneling through the Josephson.
Yes.
So it's quite amazing that now you are back to Josephson junctions, and this exponential sensitivity doesn't play any role.
Yeah, so I mean, that's not surprising necessarily. So maybe just to qualify, if I remember correctly, this was the rapid single flux quantum approach of doing. So it's not really an analog computer, but it realized on these SQUIDs, Josephson junction systems. Essentially, so if you imagine, I told you it's a pendulum, right? If you actually kick the pendulum hard enough, it will take one full round. So when it falls back, it emits a voltage pulse, which has exactly an area which is basically equal to one flux quantum. So they were going to use this to trigger the next one and basically create some kind of a Boolean logic. This was very, very popular. I also remember as an undergrad reading papers and getting very excited because I was an electronics nerd, and this looked like a very exciting platform. But yeah, it didn't work. We are not in that regime. Now there are some efforts to use this single flux quantum techniques to create cryogenic electronics as support structures for these qubits. Because a lot of the electronics which used to control currently sits at room temperature, and there is an effort to move many of these things closer. And this SFQ-based approach might be something which could be used. But very different regimes. So, people have understood the problems that we are. So remember that this is also a dissipative regime where the pendulum is undergoing. In qubits, we want to be far away from any of this dissipative stuff.
What is the current state in handling incoherent decay or spontaneous emission from the qubits?
Well, by current state, I don't know. So what has been identified is that these dissipation, basically something which absorbs the microwave energy stored in the qubits, it seems to be dominated by a collection of two-level systems, which are unwanted two-level systems in the various oxide layers which are forming on the devices themselves. So there is the fact that when you deposit this metal on a substrate, that interface is not perfect. And those defects can create mechanisms for absorbing energy. These devices are made out of aluminum or other metals which get oxidized in air. So they grow a very thin layer of oxide, and that oxide has, again, a collection of two-level systems which can absorb energy. So what has happened over the years is that people have changed the geometry of the capacitance structure so that it's as minimally sensitive to these losses, and keep the field in vacuum as much as possible. Because, vacuum is perfect. It's like the perfect dielectric, right? Second, they have looked at new materials. There is now a strong effort in using tantalum and niobium for most of the structures, except for the Josephson junction, because that's a small part that still remains in aluminum. And they seem to offer better interface qualities and also a better oxide, which seems to be absorbing less microwave power. So these developments have been happening, and that has pushed the coherence times. In 1999, where the first superconducting qubit was measured, the coherence time was 5 nanoseconds, right? Now the routinely reproduced numbers, if you look at IBM's quantum computers on the cloud, they have 100, 150 microsecond coherence times. Recently, IBM showed, I think data from one device where they had exceeded 1 millisecond in a transmon qubit. There are also these fluxonium qubits, which are by design less sensitive to the environmental losses. So basically the matrix element is much smaller. So they already have been millisecond kind of coherence demonstrated. So people are trying this, new materials, new designs to make your electric field away from the lossy parts of your circuit. So all of these things will help as we push the numbers along.
What is the largest qubit machine do you have in your lab?
So we don't have any qubit machines in our lab, in the sense that this is often people come to my lab and say, hey, show me your 3-qubit quantum computer. And basically, we don't have infinite amount of money where we do a experiment and when we keep $1 million equipment on the side so that people can see. But to be more precise, I get a lot of requests to see this. I was like, it was a 5-year-old experiment, it no longer exists, right? The largest experiments we have done so far is with 4 qubits. And we are currently building as part of a separate project where we will have this kept separately because it's funded for that purpose. We're building a full 7-qubit quantum computer using superconducting qubits. And then when it's launched, you will be able to access it just like an IBM system online as well. So currently, that's the most advanced project we are working on, up to 7 qubits.
What will be the expected coherence time for that one?
So we typically get about 40 to 50 microseconds coherence times for our routine devices. We are trying to push it a little bit more by using this tantalum technology right now. So we are hoping that we will be in the 60 to 70 microsecond range for this quantum computer if everything works out. We're still working on it. Hopefully in another 6 months, we hope to have it ready. It's actually a custom design of something we developed. It's a very strange architecture. I will probably show some pictures in my last lectures. Yeah. But it was, again, a compromise of the things we can do well versus what is required.
So you are not working with industry?
There is no industry in India which does superconducting qubits. That's why I'm only building 7 qubits, and that's itself been.
Well, no, I mean,
yeah. Yes, there will be. We hope. Yes, yes. No. So there are some startups which are emerging, but nothing has really taken off, in the sense that they will benefit more from us rather than them giving us a push, right? So it's still early days. I mean, it's the same problem of talent, right? So our best students and postdocs go to the US or the Europe. We work with what we have. And then now they have to, and this is happening in the US, right? Everybody is going to IBM and Google. People are not finding postdocs to work in academic labs. So multiply that problem by a factor of 10. There's less people here, and then who's going to start the companies? They don't exist here. So what's happening is that there are people from other areas which are trying to get in. So it's a slow process. Nothing has really taken off. There are some good startups in quantum communication, QKD, but in quantum computing, it's still very early days. There's one I heard in cold atoms very recently. They got some seed funding to get started. There is one in superconducting qubits, but I don't think they have demonstrated anything so far. But yes, going forward, I mean, you might have heard about the National Quantum Mission. So there we have to get all of these people together because, I mean, I see what you're hinting at. This cannot be built by PhD students, right? No. They cannot be wasting their time on this. If it is happening right next to them, it's fantastic because they can use the improvements in the coherence and more number of qubits to do interesting academic experiments, but they cannot be doing that. So this 7-qubit project I'm working on was sort of, I had kept saying no for the longest time, but then some arrangement was made where we found the right kind of funding and some engineers from a government lab to help us. So then we said, okay, but it still is not big enough. Still, most of the work is being done by our own people, which is partly the reason why we chose the architecture, so that we can get some science out of it and publish papers and also demonstrate something like a full-fledged system. So it's a bit of a challenge. In fact, probably the biggest challenge we're going to face is to get sufficient number of people to work in this when the opportunities abroad are also growing exponentially. I mean, I know a lot of my colleagues are facing a tough time getting postdocs now because everybody gets much better salary in IBM and Google. Yeah. You mean some Indo-US thing, or?
There is something going on.
Yeah. No, I know. I have been part of. I have been part of those meetings as well. But yes, yeah. And recently, I think IIT Bombay has become an international partner with the Chicago Quantum Exchange. Okay. All right. Thank you.